Everybody, it's my real pleasure to introduce today's CSP seminar speaker, Professor Zhong Chulier from Heist University. Zhong got his doctoral degree from Purdue University, where he worked on very complicated optical imaging problems. And then from there, I think he went to do a postdoc at Illinois with Joram Bressler. And then from there, I think he went to industry, Philips for a while and GE for a while. And then he ended up at KAIST University, where he's been for many years. He has worked on pretty much all of the inverse problems, so who knows which ones we'll hear about today. Well, image, video, and 4D today. He's won so many awards, and his most recent work related to diffusion models have thousands of citations, so it's a real honor for us to have you here today, and we look forward to learning your latest insights about guided diffusion, et cetera. So if you can click that on, that would be great. It's really an honor to have you here.
Okay, great. So, yeah, thank you very much for the kind introductions. It's really great, my honor to be here in University of Michigan to present our work. This is my second time to visit here. The last time I visited is like 12 years ago or something. Yeah, anyway, at the time still, Jeff was very kind, and this time he's more kind than enough. Yeah, so I really appreciate that, your kindness. Okay, so today, what I'm going to talk about is a diffusion models and flow model, how to control that for many image and video and 4D application. Okay. So I always thought that diffusion models is like provide some kind of probabilistic revolution in AI, which is very similar to the quantum mechanics impact on the physics, because quantum mechanics also probabilistic revolution. That's what I thought personally, but listen to in ICML, Chong Liu at UT Austin during his tutorial, he also had the same view. So I was very happy someone else is sharing the same view. In fact, actually, there is not only this high level, there's very important similarities between quantum mechanics and the diffusion model. For example, so let's think about one of the very famous stochastic differential equation expression that's used in the diffusion model for describing image diffusion process. In fact, that is actually quite often used, originally used for describing the path of quantum particles. And also, the second equation is widely used as a continuity equation in probability density dynamics. In fact, this is originated from the probability density wave, which is actually describing the quantum locations and etc. in quantum mechanics. In fact, most striking thing is, for example, in the bottom one, you see here that in these kinds of atomic model, usually the electrons has a multiple discrete energy level, and the transition between energy level is related to the exact amount of energy injection and discharge out of that one to have a correct transitions. In fact, diffusion has a very, very similar structures. We are going to talk that diffusion has very discrete manifold structures depending on during the Ford model. And in order to actually do the reconstruction based on the guidance, you need to actually be aware of these kinds of geometric structure to have a correct guidance. In fact, this is actually the main focus I'm going to talk throughout my researches. So that means what I'm trying to say is by understanding the diffusion geometry, you can actually make an easy and correct way of guiding diffusion model. This is throughout the image, video, and 4D I'm going to talk today. For those who are not very familiar with the diffusion model, I'd like to briefly touch upon the basics of the diffusion model, especially the denoising diffusion processing model or the DPM. In the DPM cases, you are basically adding small amount of noises from the images and end up with this kinds of complete Gaussian noise. And this is the easy part, but the difficult part is inversion. So you are gradually removing the noise out of the image or complete Gaussian noises. But it turns out that if time step is very sufficiently small, that transition from one step denoising can be described by the Gaussian transition with the mu theta and sigma theta. And then you can gradually remove the noise, and the final result satisfies the same image distribution as original images. Okay? So the question of this one is how to actually design this kinds of denoiser. In fact, in one of the diffusion model training is basically training neural networks such that you can actually add the noises, known amount of noise, Gaussian noises, and your network is trained to remove that noises. In fact, by adding various amount of noises for various type of images, you can actually train the neural network in a self-supervised manner. And this is actually very stable training, even compared to the GAN type approaches. So later we talk about a little bit comparison between the GAN versus the diffusion model. So this is just like adding noises, and neural network is trained to remove the noise. In fact, this part is just a scaled version of a score function estimations. This is a gradient of log likelihood function. Once you have trained your neural network in a self-supervised manner, during the reverse sampling, which is the standard ancestor sampling scheme, is gradually removing the noises and adding small amount of noises for the next level. So then why people suddenly care of the diffusion model compared to the GAN? For example, I was in the ICML in the last week, most of the computer vision related researches are based on the diffusion model, and very, very few works about the GAN. And nowadays very difficult to publish with the GAN. Why diffusion model? In order to understand that, we need to actually think about the geometry of the GAN first and what they are trying to do and what is the limitation. For example, here, GAN is, we have a G zeta is a generator, and nu is a Gaussian distribution, for example. So the objective of GAN training is from the Gaussian noises, you transport this Gaussian measure to the mu zeta through the generator G zeta. And then the dot point here and the mu distribution is the empirical distribution. For example, one point corresponds to one images of this. The goal of the GAN training is try to minimize the statistical distance between mu zeta and the empirical distribution. The statistical distance is basically averaging of all the combination, basically. So now the definition of statistical distance is usually defined in a dual form. In that case, you actually have a discriminator appears from the dual form. So you can actually have a generator and discriminator formulation. But based on this kind of formulation, you can easily see the limitation of the GAN from this picture. For example, here, this is actually the bimodal distribution. The dot point is split in two. One is a majority of the point, and the other is a minority point here, like this. Now, suppose you train the neural network in an end-to-end manner to minimize the statistical distances, because you need to actually minimize average distances. That means most of the conversion is going to be the majority of sample rather than the minority sample. So usually it ends up with not covering the other mode and mostly covering the majority of the sample. This leads to some mode collapsing of overfitting problem. For example, this is an example of the GAN overfitting problem. Now here, the left column is original image, and the second column is actually the GAN inversion. So that means you have from the images, you do find the latent, and from the latent, you generate the images again. Now, if it is well recovered, then the reconstruction should be the same as original images, okay? However, in this picture, you may see that in the second column is not exactly the same as the first one, and there is some artifact. The reason for that is GAN is usually for the face images, GAN is trained using frontal faces without hand in front. So once you train in such a way, then your image is given with the hand in front, then they try to remove it. So this is OD data, out of domain data. So the GAN has difficulties in addressing this problem. So successive processing is not working either. But in our 2022 papers, we already demonstrate this. For example, one of the nice ways utilizing the diffusion model for the image editing is inversion can be nearly perfect. For example, this is a DDIM-based inversion. In that case, from the second column, you can easily see that even though this is dialog domain data, you can clearly see the correct reconstruction, and then editing can be done very easily. So why this is possible in the diffusion model? In order to understand the reason that this is possible, you need to actually start from the discussing about one-dimensional diffusion first. So let's think about XT is actually the original image or some noise version of the image. And usually in the diffusion model, you are adding the independent Gaussian noises, and that gives a full diffusion. Now, if you learn some of the probability classes, then if you actually add two independent random variable, in the probability domain is actually basically convolution between probability density function. So Gaussian cases, probability density function is basically the Gaussian column. So you are basically convolving with the Gaussian. So what happens is like this. Now this in the bottom one here, this is actually the one-dimensional, and there is picking mode in these distributions. Now if you add noises, you are blurring out with the Gaussian corner, and eventually you end up with the one mode like this, okay? Now, diffusion model is trained by adding various amount of noise and then remove it. So that means the diffusion model is trained to learn this kinds of geometry along this data spaces and the noise variations together. So that means once you have learned those kinds of geometry, for any given, for example, random sample, it can know how to go through to arrive at the specific mode, okay? So that's why you can actually diffusion model can actually arrive at generate a different kinds of mode without concerning about data overfitting. That's actually one of the reasons why diffusion model has been so successful. Not only this one, this is 1D geometry. If you think, yeah, and also this is actually quite closely related to so-called the scale space representation, the imaging. For those, I believe most of the students are not familiar with the scale space representation because this is more like a classical signal processing. So what scale space theory, like for example, wavelet is kind of scale space theories as well. What they're doing is like this. For example, you have images. Now you actually continuously blurry with this Gaussian corner. And you have a more, as time goes on, you have a much more blurry images like this. Why do they do in this way? Now from that one, here you can actually see the global structures of the image, and this is fine detail. So by understanding these global structures and the fine detail, you can actually have a better classification, a better segmentation, and all kinds of image processing can be done better. That was actually the classical theory of the scale space in the signal processing. Now, if you think about it in that way, this looks very similar to the scale space representation, but this is in the dense domain. We'll talk about this one in more detail later after we discuss about high dimension geometry first. Now, this was actually the Gaussian convolution, convolution with the Gaussian corner in the one-dimensional cases, but there's more interesting happening in the high dimensional geometry because image is not one-dimensional. Image is, for example, 256 by 256 is it's high dimension, very high dimension, okay? I cannot know the exact number, remember? Okay, but let's think about there is an N. Now, for each images, you are adding independent Gaussian noises, right? So interesting enough, the corresponding probability density function for n-dimensional Gaussian noise is not centered anymore. It turns out it is centered around the surface of a sphere. The distance is determined by the square root n times sigma. In fact, this is very well-known theory of Gaussian set theorem. So that means that most of the noises in the discrete domain is actually centered around the very hollow spheres, okay? But still, the convolution relationship I described before still holds. So what happens is this kind of thing happens. So we have this M is actually data manifold for the clean images. Now you are convolving the sphere, which is empty inside. Then if convolving like this, then you appear some of the cylinder around this manifold, okay? And you convolve more with the noises, then it becomes a more wide cylinder and smooth it down. Eventually, what happens is, now starting from these images, you are convolving with the sphere with the discrete size, by the way. Important thing is this discrete size. We are adding the discrete amount of noises. So you end up with this kind of shell structure. Eventually goes to spheres at the end, okay? That's for diffusion. So that means in order to do the reverse diffusion, now during the reverse diffusion in the reverse processing, in the reconstruction algorithm, the diffusion model assumes some specific noise level. So that means you need to follow the reverse diffusion, which is really aligned with the assumed noise level. And by following that, you can actually have the correct reconstruction. Otherwise, if you have there is a mismatch between the assumed noise and the real noises, you mess a bit. So we'll actually see some of the example in the later. So that means these kinds of geometry is like a disk shell structures we are talking about, similar to the atomic structures. That's actually the fundamental geometry we need to consider to design an algorithm, especially a guiding diffusion model for various purposes. That's actually what I'm going to emphasize for various applications. And furthermore, if you know these kinds of geometry, in fact, algorithm design is no more heuristic. It's very easy and is easily controllable. Okay, so that means I briefly touch upon the scale space representation. So in fact, actually, this can be easily seen from the reconstruction as well. For example, in the DDPM algorithm or DDIM algorithm can be actually presented as this two-step process as well. This MT, MT minus one, and M. M is the noiseless images, and this is a different noise level. As I mentioned, there is some kinds of discrete cells. So this can be actually the transition from this cell to this one can be actually decomposed as a projection to the clean images and add denoising this amount of noise. We can do the repeating of this one, okay? Now what I'm showing here is actually this denoise version of the image during the time reverse sampling. This is from this axis to here. What you can see here, at the olive part of the diffusion model, the denoise image is a very blurry images like this, okay? And then gradually adding some kinds of fine structures as iteration going on. So you can clearly see that from the nature of the scale space representation of distribution is actually actual realization in the sample space during the reconstruction passes also follow those kinds of behavior. So this is actually the very interesting geometry, which has a close connection to the classical signal processing algorithms. Okay, now so far that's more like a fundamental understanding of the geometry diffusion model. Now from now on, based on this kinds of understanding, how to actually utilize this one for various applications. Let's start with the inverse problem first. Inverse problem is actually everywhere, especially in the medical imaging cases. For example, inverse problem, let's say Y is actually this the subsampled image and X0 is a high resolution image you want to reconstruct. And this A operator is basically subsampling operator. It can be seen from medical imaging and MRI or CT or whatever. Now, the goal of the inverse problem using the diffusion model is you need to minimize data fidelity term, but assuming that X0 is coming from the data distribution, which from the clean data, okay? In fact, this data distribution is actually coming from the diffusion file we have trained so far. So how to actually solve this problem? One of the simplest way to solve this problem is stochastic differential equation based on the diffusion of this prior information. So especially this is a posterior distribution for a given measurement Y. So what you need to do is you need to actually form a stochastic differential equation and whose score function is given log P, the posterior likelihood function, PT given Y measurement, okay? But here, because of the base rule, it can actually decompose as a prior term and likelihood term with the constant. And then after taking the gradient with respect to t, so this become a score function and this become a likelihood function like this. So this looks very straightforward. However, but there is an issue about this likelihood calculation of this part. Because actually what happens is now Y measurement is usually has a direct relationship between X0 from the X0. For example, this is a masked measurement in painting problem. In that case, a direct Markov relationship from X0 to Y. However, in the diffusion model, you are adding independent Gaussian noises, for example, to XT level, okay? There's no direct path to Y. So in order to arrive at, you need to actually have some kind of transition probability from XT given X0, and then you can actually find the path to here. In fact, this kind of formulation lead to the untractable calculation. The reason is like this. For example, Y given XT need to calculate it as a integration with respect to all x0 realization for a given xt and need to summating them together. In fact, this is actually the posterior mean of these likelihood functions y given x0. And x0 is sampled from given xt, okay? So this is a very difficult to compute. In fact, nowadays, there are a lot of actually ways, for example, Monte Carlo sampling and particle and a lot of things that have been developed. But at the time, addressing this problem was an issue. But what he realized is now, suppose instead of using this, what if we just plug in this expectation inside, okay? So this is what? This is in fact the posterior mean for a given xt. So that means in the diffusion model literatures, you can easily find the posterior mean using the Tweedie's formula. So this is a optimal posterior mean algorithm from the Tweedie's formula. So you can plug in here and like this, okay? This is actually the approximation. In fact, this looks somewhat similar to the Jensen's inequality, but however, in the Jensen's inequality, it requires that P is either convex or concave, but in this case, this is just an arbitrary probability dense function. But it turns out this is known as a Jensen's approximation. There was also several papers which tried to upper bound the approximation errors. But before I talk about that one, then what you're doing is like this. So for example, in our algorithm, which is known as a diffusion posterior sampling, now you are basically calculating the gradient with respect to the Tweedie's formula. This is functional form of the Tweedie's formula, and then gradient with respect to xt, current noise, okay? Now calculating this. So what happens is, now you are finding the functional form of the denoiser from this score function and plug in here. And there's a residual error, and this residual error is backpropagated through all of this to update this xt. So otherwise, if you actually still have a noise here, the residual error has other corruptions that lead to different kinds of gradient algorithms. So that's why you need to do this kinds of denoises formula first, and then calculate this. This is what happened. In fact, actually, as I mentioned, this Jensen's approximation can be bounded between this one, true one, versus this. And what the take-home message here is now, especially your measurement noise is Gaussian, like for example, MR measurement or some of the high dose CT measurement cases, then this is bounded in this way. And interesting thing is here, the sigma is very low or very high. This approach is there. That means high SNR or low SNR, this approximation is quite okay. Yeah. And furthermore, what you do is you have a very interesting geometry appears from this kind of DPS, manifold constant gradient. This is actually the reason why we call the manifold constant gradient. Now, if you have a measurement, we have this one is a functional form of the noise formula. Now you are calculating gradient with respect to this one. This is a measurement data fidelity term. It turns out that this gradient lies in the tangential space of the Killing manifold. That means now this is actually tangential space of this, and assuming that these Killing manifolds are piecewise linear, then its blurry version is also becoming a tangential space. So that's what's going on, what happens during the DPS sampling. Here, as I mentioned, this M0 is a ground state. This is a noiseless image distribution. This is a small amount of noise and next level noise and next level noise like this. The goal is to try to arrive at this location, and which is intersection with the data fidelity. So how to arrive it? Now we are doing the reverse sampling and then guiding based on the data fidelity term using the DPS. But as I mentioned, manifold constant gradient that allows this one lies in the tangential space. It's not deviated from the original correct manifold. So, and then do the reverse sampling and tangential space and reverse sampling, etc., and you can arrive it without deviating from this shell structure. Otherwise, if you don't do that, what happens is this guidance can go in between and it starts to accumulate the noise because assumed noise level and your noise level is different. So you can see the effect. For example, this is the effect, what happens here. For example, in the left column, here, this is actually the in-painting problem. This is box in painting, and this is 90% of pixels are missing, and this is ground truth image. If we just do this, the data fidelity term without any kinds of manifold constant guidance, for example, DDRM and the other algorithm is trying to do, then suddenly you will show up the very different images. This still satisfies the data fidelity term, but however, this is often manifold, and based on the accumulation of error, you end up with the very weird images. But however, if you have this correct manifold guidance, which guarantee that it stays in, which allow it stays in this correct geometry, then you end up with the correct images like this. Okay, so that's actually what happened. And it can be applied for other non-linear inverse problem as well, or phase retrieval, or like a non-uniform blurrings and etc. Furthermore, based on these structures, you can actually apply to the large-scale imaging, especially in the medical imaging, like 3D CTs and MRIs and etc. The problem of this manifold constant gradient for this application is it's computation expensive, because for each gradient step, you need to actually do the NFE, neural network evaluation. That's computation expensive. But however, given this kind of geometry, discrete geometry you actually have, then you can actually think about other smart way to address this problem. This is what we addressed in the last years in iClear. So to understand this, let's go back to denoising formula again. So this is a denoising and denoising and denoising and denoising. In fact, actually, what is further show is this denoising process using the Tweedie's formula is actually the projection to this clip manifold, orthogonal projection to this clip manifold, assuming this is a piecewise linear. Okay? So now, using these mathematical tools, what I can show you is a very interesting interpretation of manifold constant gradient we have shown. It turns out the manifold constant gradient with respect to some kinds of likelihood function or any cost function can be written as this part is actually the Tweedie's formula, denoise one. And this is a manifold constant gradient we just mentioned. This is a Tweedie's formula, and this is a noise image and taking gradient. But as I mentioned, this requires the backpropagation through the neural net. And furthermore, this is actually the projection, and you can further show that this is in fact the projected gradient. So that means instead of calculating with respect to xt, you are calculating the gradient with respect to denoise formula. And then this is also already in the clip manifold. And then after calculating the normal gradient and then taking the projections, then this is actually exactly the same as what this one is doing. Okay. Now, given this kind of structure, you can think about the other way. Yeah, here we just calculate one gradient for each NF, neural network evaluation. Why we are just doing that? So, but the reason is the manifold retaining in the manifold structures, because actually this is piecewise linear, then tangential spaces can be actually easily covered from the gradient, but what else? So in fact, actually in medical imaging literature, I'm from the medical imaging literature, the background like Professor Jeff Fessler. So we have a lot of actually history about optimization algorithm. And one of the very well-known algorithms is so-called the Cryo subspace algorithm for solving large inverse scale inverse problem. Here the idea is as following. We are minimizing y minus ax, okay? Starting from x hat. The goal of this cryo subspace method is now we are trying to find the solution which lies in the linear subspace starting from x hat, okay? So what kinds of linear subspace? For example, this linear subspace is actually the span from B is actually residual. By the way, this is actually assuming the square matrix A, but you can easily make it for arbitrary inverse problem. And span from these kinds of multiplications. In fact, one of the most well-known cryo subspace method is a conjugate gradient. The conjugate gradient algorithm and those algorithms always lies in this solution path iteration lies in linear subspace, okay? And also those kinds of subspaces make sense. So if you see the evolution, you can clearly see that the construction is becoming more accurate and more accurate. So that means maybe you can assume this kinds of cryo subspace can correspond to the piecewise linear manifold in the image domain. So that means now we can actually think about it in this way. So this is actually after the projection, instead of doing one gradient, you can calculate multiple conjugate gradient that lead to the better reconstruction first in the clean domain and add noises and do the projection and multiple conjugate gradient. That makes the total number of neural network evaluation much smaller because then conjugate gradient is relatively cheaper, much cheaper than neural network evaluation. So, but perhaps you may say, instead of doing that, what if we solve everything at each projection? This is what DDNM is trying to do. This works for the small scale problem, like with the in-painting and something like that. However, for large conjugate, large inverse problems, CT and etc., what happens is, if you solve that one completely, it ends up with the images which is off the manifold, which has a lot of artifacts. Then if you add noises, then you are in between in some manifold, then you start to accumulate the noises, you end up with a very weird result. Okay? So this is some of the result. So this is an 8 view. We have only 8-angle projection CT image for the 3-dimensional reconstruction. If we just utilize a filter back projection algorithm, basically we have nothing. But using only 99 iteration of neural network evaluation, this is a reconstruction. You can clearly see the very accurate reconstruction, which is comparable for the ground truth images. This one is a limited angle tomography cases. It's a 90-degree angle is missing in the projection angle. If you do the standard filter back projection, there are a lot of actual missing resolution along that directions. This is quite often used in the cone beam reconstruction algorithm or microscopic or electron microscope image. But however, using 50 NFE iterations, you can actually see that we quite nice reconstruction from the diffusion mode, as you can see. Okay, so far, this is more like I think I present this part in multiple times in different venues. So, but from now on, this is totally new. So I'm going to talk about the new stuff after we did. But however, this is necessary because, as I mentioned, this is giving some kinds of foundation why we need to think about this geometry and design an algorithm. In fact, this kind of idea can be extended for various forms of the diffusion model, like a flow we are going to talk, and also videos and 4D cases as well. The flow model, for those who are not familiar with the flow model, still maybe you may be familiar with the flux algorithm or stable diffusion 3.5. Stable diffusion 1.5, and that one is actually based on the diffusion model, and stable diffusion from 3 start to use the flux, the flow model, and flux is another example. They have a much high quality image generation from the text prompt. They have several kinds of innovation. One of the important innovation is the architecture change of the generator. So it used to use like a unit architecture for the diffusion model in the stable diffusion model in 1.5 and something like that, but they use a so-called diffusion transform architecture, which looks much more complicated. But here, the idea is this a regular structure, and they have a very much emphasis on the text embedding as well. But more important thing is algorithmic changes. So this is actually based on the flow model. The flow model, difference between the flow models and diffusion model is actually trajectory. For example, this is Gaussian, and this is actually target distribution. In the diffusion cases, because of stochastics, the target path from here is actually like this, as you can see, like a stochastic path. The flow model case, you are utilizing the ordinary differential equation trajectory, so it has a much more smooth transition, and you can actually reduce the number of steps quite significantly. So in fact, this flow model can be actually described by this kinds of simple ordinary differentiation with the VT is actually velocity field at each time point of this trajectory, for example. So as long as you learn the velocity field at each time point, you can actually solve this problem. Furthermore, but however, estimating this one in the neural network is difficult, but you can actually easily estimate this one using conditional velocity. And it turns out the gradient of conditional so-called flow matching is the same as a real flow matching. So people usually use this. And at the end of the day, especially if you use flow model what called the rectified flow, which is just interpolated version, you have very nice and very easy cost. For example, the meaning of this one is x0 is 1 point in the starting and x1 is target point. All the combination and linear combination you have tried to fit in this one. And then once you have this, then you can actually use this one as this driving force of the ODE evolution. And of course, flow model has a very important relationship, especially the starting point is coming from the Gaussian. In fact, flow velocity and score function has important relationship like this. I don't show, this looks very intimidating. However, if you think about A and BT is coming from the linear interpolation, this becomes very simple, okay? And now from here, there is a score function like this, but you can easily see that now this is unconditional score. But if you want to solve this one for the inverse problem, you can think about this is a conditional score. That means you need to actually calculate this way, okay? Now, using same kinds of base rule, you can easily say unconditional velocity field is given in this way. This is actually now using the DDS approximation we discussed before. This is coming from DDS approximation. Yeah, maybe up to now, it looks very similar to the diffusion model. Then what is new here? Perhaps you could say it's just like scaled version. But however, important thing is scale. Important thing is this scaling factor here in front. This is plot is actually showing the magnitude, the value of the score function from t equals 0 is at the beginning, and t equal 1 is beginning, and t equals 0 at the end of the reverse diffusion, the flow model. That means now what you need to do is in the flow model, what is important thing is you need to actually impose more emphasis at the early part of the reconstruction and the flow, so that it can actually guide the direction in the correct way to satisfy data likelihood function. And then at the end of the reconstruction algorithm, it reduces that amount by allowing the flow mode and recover high frequency details. Okay, this is what important key differences we can understand from this kind of derivation. In fact, actually, by doing that one, you can actually have a very nice reconstruction with the stable diffusion 3.5, combining with this inverse problem as well. But if you don't consider those kinds of like a scale of the factor, for example, here, flow shape is actually another method they try to do similar kinds of DPS type of algorithm, but just adding that one with the constant scaling factor, for example. But you can see a lot of artifact appears. But however, by understanding this close relationship between the diffusion and flow, and you can find the correct scaling factors, and by following these kinds of scales, you can actually see much better reconstruction result using the flows. Okay, then flow model-based inverse problem is actually can be solved in this way. Okay, now let's go to another different and also very important topic, which is the text guidance. So far, yeah, this is also holding not only for the flow, diffusion, also flow as well, but I mainly focus on the text guidance in the diffusion model as well. In fact, actually, text guidance is quite often used in the T2I imaging problem, text-to-image generation, or text-to-video generation as well. But one of the standard approaches to do that one is so-called the classifier-free guidance CFG. So what CFG is doing like this, during the diffusion model training, this is actually trained, as I mentioned, this is a noise estimation at this noise level. So what they do is like this. Now, for example, we have a CAD images like this, and now corresponding aligned text image like this. And then once you have aligned this one, you can estimate additive noise compound. They train in such a way. This is a conditional training. Of course, they can use unconditional training as well. With the null text, they try to estimate the noise together. Once you have this conditional train and unconditional train, at the inference time, they use so-called the classified free guidance. Classified free guidance is like this. For example, here, this epsilon epsilon null is actually with the unconditional training without any text, null text. And this epsilon C is with the text condition. Now, suppose we are actually trying to generate the image with the Tyler shape trapped, blah, blah. This is text to image generation. Then what people do is you are doing the linear combination of this and then choose some of the scaling factors, CFG parameter, especially like a 7.5 is quite often used. And the original reason people use this CFG guidance is now if you actually have this one, this basically corresponds to this peaked distribution with the omega lasers like this. So that means their distribution changes from the original distribution and try to sample from this peak distribution. But this is quite heuristic in some sense. And also it turns out that omega should be very high to make it correct guidance. And it introduces a lot of issues, especially in the inversions as well. One of the artifacts we can easily see here is this kind of saturation artifact in CFG. For example, as I mentioned before, this kinds of the neural network, the diffusion model is kind of scale space representation. It should generate from the low frequency to high frequencies, right? The picture I show you is actually coming from the CFG++, which I'm going to talk. But if we just utilize the CFG, at the earlier part, we have very saturated images and gradually saturation reduce and end up with the images. So this kind of saturation phenomena happen at the early part. Why those kind of things happen? In fact, in our recent paper at CPR, what we call the CFG++, what it demonstrates is now this kind of text guidance can be also formulated as a manifold constraint guidance as well. In fact, the idea is very simple. Just utilizing the same tool we actually use for the inverse problem. We have a loss function. Now this loss function is coming from the so-called the score distillation sampling loss. This is a conditional epsilon matching loss here, okay? Now you try to minimize this one while you are sampling from the unconditional distribution. You start with unconditional diffusion model, but during the iteration, you try to minimize this conditional score distillation sample. Then you can easily show that the corresponding result can be written as updated result is given by the linear interpolation between Tweedy's formula from the unconditional sample and conditional sample. In fact, it's a linear interpolation in between. But if we use a large number of omega, the formulation is exactly the same, but it turns out it's an extrapolation. That means now, given our manifold geometry, now we can easily see that X null and X conditional image is already trained in the diffusion model during training phase. So they correspond to the manifold structure. But this extrapolate values, there is no guarantee it actually lies in the correct manifold. Correct way of doing this is assuming the piecewise linear, it should be interpolation in between, okay? So based on that, you can actually have a very simple correction. The left side is actually the original CFG, and the right side is a CFG++. Yeah. If you see here in two sides, it looks very, very similar. It's very difficult to find the differences. In fact, the only difference is in the last line. If you see here, this noisy part, this noisy part at the end, that's actually coming from the unconditional score function noise. But in the conventional CFG cases, it's coming from this combined cost. Okay? So that means by just simply changing this part, you can make a significant differences. And furthermore, because of that, now you can use lambda as an interpolation value between 0 and 1 to make it whatever you want. For example, this is some of the example we actually demonstrated. For example, left one is generated the same, exactly the same prompt with the CFG. We may see notice some artifact in front of the canoe, but you can have a very clean construction because we have a much better text alignment. Furthermore, this is inversion process from the source images and the CFG-based inversion. 0.0 with the omega scale, you can do the somewhat similar inversion, but if you do the large 0.2 or 2.0, this image is not same as the original image, right? But in the CFG++ cases, you can actually have a very similar inversions. Okay. Now utilize, and furthermore, if you see the trace of the reconstruction, you can also see a lot of at early part of this one can be actually set, easily moved and etc. And also you can do the much improved text alignment and inversions as well. In fact, the CFG++ algorithm is already implemented in the community. For example, Comfy UI and those things quite often used for the Stable Diffusion community and the designers, and they have an option for the CFG++ right now to utilize that for theirs. Okay, now based on this kind of understanding, you can do a lot of interesting extensions like this. For example, one of them is actually simple extension, what they call the video guide. The idea is like this. Now, as I mentioned, we basically have minimizing the conditional diffusion epsilon matching by using the unconditional evolutions, okay? So you can actually use similar ideas for solving this problem. This is actually a video generation problem, but there are multiple like a video, open source video models currently available. Nowadays, there are very good models, the open models available, but before that, actually, the video crafter or animative is one of the nice work people use for the open video generation. However, there is a pros and cons. For example, video crafter has difficult to control the style and content, but it's actually has a good temporal resolution. But however, animative, that's originally coming from the image diffusion model and then temporal plugin inside. So it has a very good control of the style, but there's a poor temporal resolution. You can see that. So how to actually utilize this kind of two ideas? The idea is very simple, exactly the same as a CFG++. So CFG++ cases, this loss function is coming from the conditional score matching, right? And then our evolution is starting from the non-conditional one. Now here, what we're doing is now we consider this temporal consistency as a guidance problem similar to the CFG++. So we are using the external video model, which has a very good consistent temporal consistency as a guidance, and minimize that one as a loss function that the loss is n. And then we are evolving with the animative, which has a high, easily controllable. So then it turns out it's actually the combination of the two during the 2D formula. And of course, there is some kinds of like low pass filtering goes on, some engineering goes on, but the key idea is basically using by simple extension of that idea. But you can see very significant differences here. This is actually the video generated with the prompt in front, and the left one is animative. You can see that temporal consistency is not good, right? The glasses changes, but you don't see those kinds of changes. Similar kind of thing happen. Here, same prompt, you can see the temporal consistency is not good in the original animative, but you have a very nice consistency in this generated images. Same thing, suddenly the shape changes, but nothing happened like this. And even these pictures, okay? And even this high speed races, if you see here, the structure changes, but doesn't change this in this way. And a similar thing happened. And like this. And also even see some of the weird thing happening in here, but those things never happen. Okay, I can quickly skip over. Okay, now that means actually those kinds of external guidance works. And now for the, we already used 50 minutes. I just wrap up in 5 minutes. Okay, so I talk about some extension for the video inverse problem as well. In fact, we so far discussed about the inverse problem for the images, but we can actually extend this one easily for the video inverse problem. But one naive way of approaching this problem is using video diffusion mode. But that's what we want to try to avoid because there are not that many, oh, sorry. This is time to close.
It's still on Zoom. It's still fine on Zoom.
Yeah. Okay. It shows up. Okay. And I put this one out. Okay. Okay, so okay, so our goal is instead of using that one, we are interested in solving the video inverse problem using the image diffusion model only. So in fact, we have a series of paper which is in iClear this year, and another one which is extended to the large scale latent diffusion model in ICCB. So this is called the Vision XR. The idea is following. Now, to solve the video inverse problem, there is a multiple temporal frame, okay? Now, the key idea is we are basically doing the denoising separately, but once correcting the old temporal frame, the image inverse problem can be done in the 2D denoise domain at the same time, and then do the denoising, and this is follows like this, okay? This looks like a simple, but however, if you just apply this one in ordinary image diffusion, it never works. The reason is following. Now you start with the same different noise level, which is the independent noise at its time point. In that case, even though we are controlling in between, it generates different kinds of images. There is a difficult to do the synchronization in between, okay? But suppose if we just start with the same noise level, it generates exactly the same image because its noise determines the final result, okay? So what you do is, in our paper is actually, now we start with the same noises. This is what we call the batch consistent sampling. And then during this reconstruction part, they try to, using the data consistency, they try to actually decorrelate the temporal denoising by satisfying the data flow. And they start to depart and then adding similar amount of noises, same noises, and do converting in this way. And now you can actually control the temporal consistency through the same noises, but however, solve the inverse problem using the denoising domain. For example, this is image we actually demonstrate. For example, the left one is a temporal blurred images, and the right column is actually reconstructed images with 1280 by 768 images. And this is temporal blurring plus in-painting problem together. And you can see a clear reconstruction like this, and similar things like this. And just see a lot of example, which can be easily working with this algorithm. And also computation time is much quicker because we don't use sensitivity diffusion mode.
These are like super resolution. What's the inverse problem here?
Here, this is temporal blurring, temporal blurring plus spatial blurring together, and spatial in-painting as well, for example.
Okay.
Yeah. And this is with the in-painting and temporal blurring together. Okay. And also another thing actually I'd like to show is now this is actually the inverse problem, but another type of inverse problem is actually for the interpolation. Interpolation problem-wise, actually, this one is difficult to solve using the image diffusion model only, but however, very simple way to address this problem. Here, this one is, for example, you have start images and end images. If it's closed, then you can easily do the interpolation, but the thing is, it's very different or very far. When something is moving very fast, and how to do interpolation. In fact, one of the approaches to address this one is actually using the stable video diffusion model. It's a so-called time reverse diffusion. The idea is like this. Now we have a one frame and end frame, and you have repeated and add this one, okay? And then do the denoising, and now you do the time reversal, and you have an end frame repeated, and do the denoising and time reversal and adding them together. And the manifold structures, what they do is they do the denoising and they do another denoising and then fusing them. You can easily see that if this one and this one is close, then this linear interpolation is okay. But in video cases, this image and this image could be quite far. then maybe there is an interpolated image could be out of the manifold. So that introduced a lot of artifacts, as we show you later. So they actually have a lot of ad hoc and heuristic approach to compensate for those kinds of artifacts, okay? But however, given these kinds of manifold structures, understanding of the manifold, you can think about more easier fix and simple fix. That means now you denoise first from one dimension, forward direction, and then time reversion, and adding noises, and that's also manifold, and then do the denoising for the time reversed image. Then this is again, both of them in the same manifold, but satisfy the both conditions. Okay, you can do this one alternately for each time step. Very simple fix. Now you can actually clearly see very improvement here. This is a start frame and end frame. For example, TRF, you can see something is weird thing is happening, and this is generated in between. And now this is a vivid sampler. We actually see this is much more realistic. You can see some, yeah, this is actually more example. This image and this airplane image. Now, if you actually see TRF, suddenly airplane appear. This one is like this, yeah. But now, vivid sampler, you can clearly see the correct way of airplane is interpolating between. And this is also very interesting example. This frame and this frame, for example, TRF, you may see a lot of artifacts in the generating between the, there is a somewhat destruction going on during the, but however, in this way of manifold constraint interpolation, you can clearly see nothing happens and you have a correct interpolations. And same thing here. Okay. So should I stop here or?
We have 5 more minutes.
Okay, yeah, and maybe this 4D is also exciting, so I can show you some 4Ds and then stop it. Okay. And here in this project, what I want to do is generating videos at different view. In fact, there are a lot of those approaches appears. For example, this is usually coming from the large vendors, but generating multiple view at the same time from the beginning, from the same text prompt. Or for a given input video, they try to generate a different camera angle like this. That's actually what I mentioned about K-pop movie in the different angle. Okay. Okay, but here what the people do is they usually do a lot of pre-training with the multi-view video data. So academic environment is very difficult because the problem is those data sets are very rare and also very small. In order to actually do that, what vendors is doing, they do a lot of simulated engine to generate this kind of simulation and videos, and then try to use that one for this impending problem, the multi-view, and train that model. So our goal is, we originally started with this paper, which accepted in ICSB. We just start with the similar kind of idea. It's a one image, one shot image. We have a one video. And the idea is basically fitting that images at a different initialization and to generate images. This is working, but yeah, from a context that I'm talking about, it's a little bit different. But I can show briefly the images here. For example, this is the input video. Now you can see the orbit up. You start to see the background of and you can actually see different part if you do the camera, right? But still, this requires optimization. Now, is it possible to actually do generating these 4D videos without any training, zero shot? In fact, this is possible based on our understanding of the geometry of the diffusion model and especially manifold structures. In fact, actually, if you think about this problem, you can see this problem can be actually considered as an interpolation or extrapolation in the 4D grid. That means this is time axis is actually the video axis, okay? Video time axis. And camera axis is a different camera angle, for example, okay? Now, if you have a given video, now you have a one line filled from given video. And goal is to fill in all other part. So how can you do that? One thing is actually, there is a very well-established off-the-shelf model for the depth estimation. And using the depth estimation, you can actually generate the different camera view first. But there are a lot of parts missing. So you need to do the imprinting, but that kinds of imprinting can be done using the vivid sampler with the adding noises, with the initialization of that one. You can actually do what we did in the vivid sampler to fit in this column. Same thing here. Now we have two end frame. You can use the vivid samplers again and to interpolate in this one, okay? And now this is the initialization. Now what you do is, now from here, the consistency is very important because we are generating the 4D video, but that should be consistent in every view and every time angle, okay? How to make the consistency? It's the same idea. You are doing the bidirectional interpolation, in this case, a 4-directional interpolation. So at each iteration of the diffusion sampling, you do one direction on this way and direction this way, one direction in this way, and one direction this way. And then you are gradually denoising by doing the denoising in that way. This is some of the result. For example, here, this is input video. And the output is actually all be right. Camera is rotating left and right. And more important, more interesting is this never was possible in other kinds of video generating model. This is all with bullet time view. Because we are now having a 4D grid already, you can fix one time and see the video along that camera angle. So you can see this is fixed and you can actually see the camera rotating from the input generated videos. This is another example, for example, from the input videos, you can actually generate different angle videos and also orbit bullet time videos as well. Yeah, I think I need to stop here. And in fact, yeah, I can skip all. Maybe if you're interested, then maybe I can talk during the internet. And in fact, actually, I believe this diffusion model is really an essential tools in modern video image and 4D processing. And the take-home message I try to emphasize over and over again is understanding geometry, it make your life easier to do a lot of applications much easier without doing any kinds of heuristic manipulation. With that, I'd like to conclude my talk. Thank you very much.
Thank you very much. We have plenty of time for questions.
Yeah.
I have a question. So thank you for the great talk. So my question is, so you mentioned about applying the diffusion models and flow matching for inverse problems. So I wanted to ask whether you have applied these models also for some medical image reconstruction, such as MRI or X-ray CT.
Oh,
and
yeah, that's I already showed you, for example.
Specifically, I'm talking about like dynamic imaging, because you mentioned about the video.
Oh, dynamic imaging. I haven't tried that. I haven't tried it yet. Okay, dynamic imaging, that might be interesting topic as well. I used to work on the cardiac imaging before, but yeah.
Right, because in cardiac imaging, it's very critical to reconstruct the image of the heart and how the heart motion is changing over time, right?
Yeah.
So according to you, how would diffusion models or flow matching would be able to match the performance of other supervised models in reconstructing such motions of the heart?
That might be interesting topic, especially if you can use, for example, 2D diffusion model for the temporal dynamic imaging. I think there's a chance actually you can do a lot of interesting new things. Yeah. I think you could actually extend that. Yeah. Yeah.
Thank you so much for the fantastic talk, Dr. Ye. So I want to also follow up this question to ask more about your thoughts about like the large-scale inverse problem solving. So like in the DDS paper, you also show like 3D image reconstruction. If I remember correctly, that is also using the idea from the MBIR, using the 2D diffusion prior to some of the 3D.
Oh, you mean the extending to the other direction? Okay.
That is also something I can see from like solving the video inverse problem, like using the 2D diffusion prior, and then to solve this with the consistency in the noise or the consistency of the manifold. I wonder, like, from your opinion, like if you want to solve the large scale or the high dimensional inverse problem, so even though we can see the promising results from this kind of approach, do you think this is the current standard way we're doing, or is there any other we can go beyond using only the 2D diffusion prior, or even to train the other kinds of the diffusion priors, and that could be.
That's a good point. Actually, we used actually as so we used to use MBIR in the G direction. That's actually Hyungjae's paper, original paper. But after that, we actually had some kinds of perpendicular way of doing that one as well. But both of the especially perpendicular is very time consuming. But at that time, the video model using like a video diffusion using the image model is much later than those work. But currently on my thought, maybe similar idea could be go back to the volume reconstruction as well. Yeah, so we haven't tried it, but I think it may work. Yeah.
You mean like still using the
2D diffusion,
use the noise consistency?
noise consistencies, and also and these kinds of deblurring along that direction. The math, that may work. Yeah.
And I think you also just mentioned something, but was interrupted by the technical issue. So you say like we don't want to use the video diffusion model, generation model as a prior to solve that. Did you see that?
Yeah, in fact, the inverse problem cases, that was actually our original goal, because inverse problem for the video, usually many of the video inverse problem we are dealing with is high resolution videos, okay? But there are not that many high resolution video inverse, open source video inverse, the video diffusion models are available for, of course there is an in-house model, but that's difficult to use. But there is no open models which is available. So that's why, but however, stable diffusion and flux are already available. So you can manipulate and modify very easily. So that's why this is a permanent solution, I would say. But however, it's so much faster, of course. But however, for those kinds of video interpolation problem, 2D is not enough. You still need a 3D diffusion model. Fortunately, stable video diffusion is open source available, so we can easily modify. That's actually what it uses, 3D video diffusion interpolation. Yeah. But other than that, inverse problem-wise, high resolution is actually difficult to use. Yeah.
Thank you so much.
I have two questions. The first is when you showed the flow matching with text. So how important is the prompt? I know you showed results with the same exact prompt, but the quality of the prompt, how much does it impact the reconstruction quality?
Oh, that's a very good question. And in fact, actually, we have a multiple of those papers to address related problem, and which one I didn't actually present here, even though I can actually, maybe in the meeting, I can show some of them. There is, in fact, a two-way of addressing these issues. For example, prompt optimization. So starting with the initial prompt, we actually had a paper so that actually optimizing during the iteration to minimize this result as well, or maybe just give them prompt and try to actually add that as a regularization during the reconstruction as well. There's a multiple way. Or listen one, which I skipped, is actually, instead of doing the prompt optimization as a whole, you can actually have a placeholder at the end of the original prompt, and just optimizing that part gives a much better result because we still retain the same semantics, but utilizing that placeholder string toward your goal. Yeah, that's actually what you can do. Yeah.
My other question is about the temporal. You showed some starting from some manifold going to the M0, and then starting from the same noise.
Yeah.
There was like maybe I missed that. There was a yellow arrow where you're showing that they could be kind of separated. So my question is like how the temporal how do we make sure that there is no artifacts between these slices?
Okay, that's a good point.
Yes.
You're talking about this slide,
Yes,
right?
exactly, yeah.
In fact, this part is coming from here. So you solve this optimization problem. Y is actually your temporal measurement, which already has a temporal consistency, and A is already given known as a temporal blurring, for example. Then you have a initialization from something which looks very similar. But if we solve this problem in some conjugate gradient method, you can actually make the reconstruction diverges a little bit, but still consistent, coherent, but has a different kinds of, yeah, you are gradually imposing this kinds of measurement consistency. That's actually given in this way. So it's not exactly the same point,
Yeah.
slowly diverging, but still is a temporary consistent.
I have a follow-up question for this. So you're adding the same noise to all frames to try to preserve temporal consistency,
Yeah.
right? So that feels a little funny to me because if we just try to do 2D image inverse problems, we don't add the same noise to every row of the image to try to keep the rows of the image consistent. We rely on the prior to keep the rows consistent, right? So is this a sign that our space plus time diffusion model is not quite good enough yet, that we need
Because this is, we are not using the space-time diffusion, 3D diffusion. We are just using the 2D diffusion model.
That's what I meant.
Yeah, that's
Okay,
right.
I
Yeah.
see. Yes,
Yeah.
then you need, yeah, okay. If we had a true space-time
That's right.
diffusion model,
Yeah.
we shouldn't need this trick,
No,
right?
no,
Okay,
yeah.
thank you.
Thank you for the great one. I have a question about the scale of the guidance term. This is a hyperparameter, right?
Yeah.
How we should choose that hyperparameter? Is there an optimal way
You mean the guidance in CFG or in the general inverse problem?
in the general inverse?
Okay, that's a good point. Okay. That's why, as I mentioned, that this guidance parameter, the actual absolute value itself is tunable parameter. But this is important here, for example. Where is it? Oh, yeah, the previous one. Okay. This kinds of trend along this during the evolution of the temporal evolution. Diffusion model started from t equals 0 and 1 to 0. But here, this is relative guidance scale. Okay. At the early part, we have a more guidance, and the later part is small guidance. The absolute value of the guidance scale, you can actually still choose. But here in our cases, we just, yeah. I'm not sure he chooses it, he just followed this one or not. But the important part is this kinds of relative scale is very important. And just hyperparameter, absolute value and hyperparameter can be actually easy tuned. Yeah.
I have a follow-up question for the full DPS. Because the original problem and the flow matching model is still using the guidance, the text prompt guidance diffusion model. So is that possible to extend to the model without the text guidance case? And I read your paper for the 3DIP for the out of data diffusion generalization problem. For the flow matching can be also integrate the similar idea.
Oh, yeah, if I understand your question correctly, that, yeah, we have a paper that we trained the diffusion model that's without text in that case, a VDM, no, the VDM, the EDM. And for one distribution, for example, with the synthetic data. And then during the reconstruction, we can actually feed into the data for the unknown distribution for the OOD data. So that's why we have some paper. We have one paper regarding that issues. But the question is how to actually extend this one for the flow model case. I believe the same kind of things is possible. Furthermore, what I believe is based on understanding of the prompt optimization nowadays. At the time, we tried to actually fine-tune the model during the iteration, but perhaps instead of doing that one, we can actually just do this kinds of like the flow the text optimization. Well, maybe I can. This is good time to show which was missing. Yeah, for example, I can show you here. Okay, this one. Here, what the goal is actually many of the video inverse video generating model, the temporal consistency is not working very well. Okay, there are some issues of temporal consistency. So what it did is actually, as I mentioned, there is a placeholder at the end, and we now optimize this placeholder as, for example, here, and by satisfying some temporal consistency, loss. This is usually based on, in this case, it's optical flow discriminator. We choose random set of the video frames and check whether the optical flow is correct or not. And based on that loss function, we actually change this one, okay? But cool thing about this one is, now once you have this prompt only, it can be applied across all the frame. You don't need to do frame by frame, for example, DPS algorithm. That's time consuming. And also, you don't need to do the frame by frame fine tuning of the diffusion. We just change the prompt based on optimization. But it works very well. For example, here, left one is baseline, and the right one is based on just like a prompt optimization. Still, you can actually have a temporal consistency. And also, this is some other examples here. The left column and right column, if you see there, you can actually have a better temporal consistency, for example. Yeah. So that means prompt optimization seems to have a very interesting way of handling this all the data so at the inference time. So, yeah.
That does not need like to fine tune the parameters, right? It's only the prompt.
Prompt, so yeah.
And the prompt that is optimized, is it interpretable to the end? Can you
Oh,
map it back, or is it just a number?
Oh, that's a time to show another thing. I skip here. For example, here, in this one is actually, for example, this is a minority sample generation. So that means from this is usually, the left column is usually most of the majority sample. But we have a placeholder, as I mentioned before, at the end, okay? And then starting from that one, we actually do the maximizing the minority criterion loss function to optimize this, okay? But what's really interesting here is now the placeholder, depending on when you initialize a placeholder, you have a very different kinds of behavior. For example, you initialize that one as a prompt with the dirty, and then you start to optimize that one, but it ends up the minority with the looking dirty. And with a random initialization, yeah, this is another minor sample. So that means there is some kind of semantic control capability depending on the initialization as well. Yeah.
All right, well, he'll be around all day. Many of you have meetings with him that you can ask him further questions. So let's thank Dr. Ye one more time.
Okay, thank you.
Pause on Zoom.